Welcome back in, everybody. In this video, we're going to look at analysis of variance and go step by step through one of these problems. Of course, analysis of variance is often nicknamed Anova for short. And let's look at this problem. So use Anova with alpha of 0.05 to determine if there are any significant differences among the following three treatments. Calculate a measure of effect size, and conduct Tukey's post-hoc test to determine which means are significantly different from one another. Okay, so the first thing to consider is what is analysis of variance, and essentially it allows us to look at mean differences between two or more groups. And so recall back in the discussion in chapter 10, which was independent samples t-tests, we were only able to look at two different groups. For example, men versus women. Now we can look at three groups or four groups or five groups, etc., in order to check if there are significant mean differences between those groups. And so in this problem right here, we're going to look at an example with three different groups. Each group has 4 participants, and they each receive some different treatment. So the first group receives treatment 1, the second group receives treatment 2, the third receives treatment 3. The question we're trying to ask here is there a statistically significant difference in the means between these 3 treatments? And if there is, well, which groups are different than which? And also, how big is the difference? We're going to measure effect size. So generally speaking, we have to do a few different things. So the first is just the Anova. Recall from in the module as well as in the textbook, the Anova itself simply tells you whether or not group differences exist, but it does not tell you where those differences are. That's why you need to conduct a post-hoc test. Post-hoc tests are done after the initial Anova test in order to determine where the differences are. So if a difference exists, it might be between treatment 1 and 2, or treatment 1 and 3, or between treatments 2 and 3. That's what post-hoc tests are used to figure out. Okay, so we have this basic information. This is the raw data. So some researcher went out and measured 4 people in the first group, 4 people in the second group, and 4 people in the third group, and obtained these scores. What I've actually gone ahead before beginning this video was calculated some necessary information to actually conduct the Anova. And so let's go through that with the first group, treatment 1. So the first is M, which is the mean, the average score, which is 3. Then you get T. Recall that T stands for the sum of scores within a treatment. So if you add up these 4 scores, you get 12. And then finally, I have the sum of squares, SS, for this first group, and that equals 8. If you don't remember how to calculate sum of squares, go back to chapter 4 because it is important. And I've done that for all 3 groups. I have the mean, the sum of scores, which is T, and SS, the sum of squares, which is 1 for group 2. And then for the third group, it's 49. Okay, down here I have just a few more pieces of information. N, capital N, is the number of people in your entire study. So 4 here, 4 here, and 4 here gives us 12 total. G is the sum of all scores in your entire study. So when you add up all 12 scores, I get 84. And then finally, if you square every single score and then add them all together, you get 904. So how did I get that? I took 3 and squared it to get 9. Then I took 5 and squared it to get 25. And then 10, squared that to get 100. Do that with all of these scores, add it up, and you get 904. And that value is going to be helpful later on. Okay, so essentially, let's talk about the hypotheses. The null and alternative hypotheses are fairly straightforward for the ANOVA. And it's going to look something like this. The null hypothesis is essentially saying that population mean 1 is equal to population mean 2, which is equal to population mean 3. In other words, you're saying that there's no difference on average between the populations that these people came from. They're all the same, no difference. On the other hand, the alternative hypothesis is stating that there is at least one mean difference. I'm just going to put that right here. All right, so that is saying that no, they're not all the same. At least one of these groups on average is different than the others. And so now our goal is to determine which of these two hypotheses is more likely to be the case. And so we do that by analyzing variance. Now, there's all of the variance in the study, which basically is the idea that among these 12 people, there's differences among them. They didn't all have the same score. But we're going to take that total variance and essentially break it up into two kinds. The kind that goes between groups and the kind that goes within groups. So here's what I mean by that. Within group variance. Let's look at just this first group, treatment 1. Now, these 4 people did not have the same score, yet they were all treated the same. So we call this within group variance. Within group variance is just random variance. It has nothing to do with your treatment effect because these were all people who were treated the same. So the fact that they all received the same treatment yet had different scores is just attributable to random error. Just non-systematic noise, if you will. But on the other hand, look at the differences between groups. So take a look at the averages, for example. The mean for group 1 was 3, the mean for group 2 is 4.5, and the mean for group 3 is 13.5. There's differences on average between these groups. And so that is going to be related to the treatment effect, the idea that these groups were treated differently, and that might cause a significant difference in the average score between these groups, not due to random chance, but due to the actual treatment effect itself. And so that's what essentially our test statistic is comparing. If you look at this formula for F, which is the test statistic for ANOVA, MS between is your variance between groups, MS within is your variance within groups, and you're simply comparing them and getting a ratio. The larger F is, the higher likely it is, the higher chance it is that there's a statistically significant difference between groups as a result of the treatment effect. Not sampling error, but the actual treatment effect. Okay, so there's a ton of formulas to think about. As always, the good news is you don't need to memorize formulas. And I also argue that this is not as complex as it might seem by simply looking at these formulas. And what I think is actually beneficial is I like to start with my degrees of freedom. So let's go ahead and calculate degrees of freedom formulas first. And they're relatively, simple because you're just plugging values in. So first and foremost, let's look at DF total. I'm going to put DFT for total. And the formula is right here. Take your total number of people in your study, which was 12, and subtract 1. So that is 11. 12 minus 1. Next, let's look at degrees of freedom within. I'm going to put a W for within, DFW, degrees of freedom within. The formula says essentially take the degrees of freedom in each group and add them all together. So n minus 1 for each sample. So the first treatment, the first sample, there are 4 people. So 4 minus 1 is 3. For the second group, 4 minus 1 is 3. And for the third group, 4 minus 1 is 3. So 3 plus 3 plus 3 means that there are 9 degrees of freedom within for this analysis of variance, for this ANOVA. And then last but not least, we can calculate degrees of freedom between. And you have some options here. So first, I think the easiest thing is k minus 1. All right, what is k? K is discussed in the module as well as the textbook. K is simply how many groups you have, how many treatment samples you have. So we have 3 groups, so K is 3. So if K is 3, 3 minus 1 gives us 2 degrees of freedom between for this analysis of variance. Now, although we used this formula, we didn't actually have to, because we had total degrees of freedom, and total is always broken up into within and between. So note that 2 plus 9 is 11, and that's your total value. So once you have 2 out of the 3, you can always find the third. Okay, let's move on now to our sum of squares values for this study. And let's start with SS total. SST for short. All right, and then we're using the shortcut formula, and let's go ahead and use that first, and then talk about what you would do if you actually wanted to do the long way. We're not going to do the long way, but I'll explain how you will if you want to. It's always nice to do, to know how to do it both ways. So it says, take the sum of all scores after they've been squared. So the squared scores added together, which was 904. And subtract g squared, 84 squared, divided by how many people are in your study total, which is 12. Okay, so let's go ahead and calculate this value. I'm getting a value that I need to double check because it looks incorrect. Always double check your math. Okay, 316. 316 is the sum of squares total for this analysis of variance. That's this shortcut formula that our textbook uses. Now, if you did not want to use that formula, how would you go about getting your sum of squares total for the entire Anova? We have 12 scores. Essentially, you would put them all in one row. So you have 12 scores in a row. Calculate the mean, and then a new row where you have deviation scores, which means you're subtracting the mean from all 12 scores, and then a new row, a new column where you are squaring all of those deviation scores, and then the sum of the squared deviation scores is going to equal 316. All right, so obviously the shortcut formula is nice and saves a little time. The next value we can calculate is SS within for the entire analysis of variance. So what the formula says is take the sum of squares values inside each treatment. What that means is simply take the sum of squares for each sample and add them together. So for the first sample, it was 8. For the second, it was 1. And for the third, it was 49. So 8 plus 1 plus 49 looks like 58. All right, now SS between. And the thing about SS between is now that we have our total value of 316 and our within value of 58, sum of squares between is going to be 316 minus 58, which is 258. Okay, we have 6 calculations done. There's 3 more to go to complete our F statistic, our test statistic. So the next values are these MS values, which stands for mean squares. This is basically a measurement of how much variance is between groups, MS between, and how much variance is within groups, MS within. And so let's go ahead and calculate each. MS between is SS between divided by degrees of freedom between. And that's 129. And then MS within is SS within divided by DF within. So 58 divided by 9. 6.44. And now we can calculate the test statistic, F. Let's calculate it and then interpret it. So MS between on top, the numerator, 129. 6.44 MS within in the denominator. We get 20.03. So here's what this is essentially telling us. The variance between groups is 20.03 times larger than the variance within groups. Remember that the variance between groups indicates what's going on as a result of the treatment effect, whereas variance within groups tells us what's going on as a result of random chance or random error. So the systematic stuff, the interesting variance, is 20.03 times larger than the non-systematic variance or the random variance. Now, 20.03 is a very large test statistic, but we always have to compare our test statistic to a critical value of, in this case, F. And so we need to go to the Anova table, which looks like this. And to read this table, you need two pieces of information in addition to your alpha level. So over here it says degrees of freedom numerator. This is what is your degrees of freedom in the top, the numerator of your F formula. And so if you go to your F formula, that is your between value. So DF between is 2 in our study. So we're going to look at this column, 2. And then over here it says degrees of freedom in the denominator. And that is how many degrees of freedom are within. So because the denominator of your F statistic is the within value. So DF within we calculate as 9. So 2 and 9, here's 9, here's 2. They match up right here. And the instructions at the top of the table, it says, for an alpha of 0.05, use the light face type. And for alpha of 0.01, use the bold face. So our question says to use alpha of 0.05. So that means that our critical value of F is 4.26. Critical value is 4.26. Our test statistic is much larger than that value. And so our conclusion is reject H0. In other words, the data suggest there is a statistically significant difference in scores between these three treatments. Now, recall like what I was saying at the beginning is now we know that these groups are different from one another, but we don't know which groups specifically are different from which groups. All we know is at least one mean difference exists. We're going to use the post-hoc test in a moment to determine which groups are different. But before we do that, let's just calculate effect size real quick, which is eta squared. And eta squared is your SS between value, 258, over SS total, which is 316. Gives you 0.82. And the cutoffs for the interpretation are the same as R squared. So 0.25 is large. You could call this very large. There's at least one mean difference between the three samples, and that difference is very large. All right, we don't know yet, though, which groups are different from which groups. So I'm going to erase the effect size calculations because we're done with that. And I'm going to focus now on this final formula down here, Tukey's honestly significant difference, HSD. And to use this formula, you need your Q table. So this is what the Q table looks like. The textbook calls it the studentized range statistic, but let's just call it the Q table for short. And this provides you with probability estimates for how big the difference between samples needs to be in order to be statistically significant. In other words, we're going to calculate one value called HSD, and we're going to use that value to compare two groups at a time. So for example, group 1 versus group 2. And if the difference between these two groups on average is larger than our HSD value, we are going to claim that that is a statistically significant difference. Okay, so let's calculate HSD. And the first thing we need is our Q value. So to read Q, the Q table, you need a couple pieces of information. The first, it says K. Recall that K is the number of treatments. So we have 3 treatments or 3 groups in our study. So that's 3. This over here says DF for the error term. The error term is DF within. Essentially, that's the denominator of your test statistic, which the within value goes in the denominator, which is the error term. So DF within was 9. Okay, so 9 is right here, 3 is right here. They match at these two values. And again, just like in the Anova table, if you're using an alpha of 0.05, which we are, our value is the light face one, 3.95, whereas use the bold face for 0.01. But we're using 0.05, so that means our Q value is 3.95. We multiply that by the square root of MS within divided by N. MS within was 6.44. And lowercase n is 4. Now, before we calculate this, just a couple notes about this. So one of the disadvantages of Tukey's post-hoc test is that it requires equal sample size. You have to have the same number of people in each treatment group. If you don't, you cannot use Tukey's test. You have to use an alternative like Shefe, which we discussed Shefe in the module. But I guess a quick side note, this is arguably the most popular post-hoc test. And so I think the reason it's so popular is that it's relatively simple, as you'll see in a moment. But the issue is you have to have equal sample size. Unfortunately, we do. Okay, so let's go ahead and calculate the HSD value, which I'm seeing as 5.01. Okay, so let's see what we have to work with here. What this value is telling us is that the mean difference between any two groups must be 5.01 points or larger to be considered statistically significant. So let's look at treatment 1 versus treatment 2. Treatment 1 had a mean of 3, and treatment 2 had a mean of 4.5. And I don't care about the negatives. It's only absolute value. The absolute value is 1.5. There's a difference of 1.5 on average between treatment 1 and treatment 2. That is not larger than your HSD value. So that is not significant. NS for not significant. Groups 1 versus 2. Let's now look at group 1 versus group 3. Group 1 had an average of 3, and group 3 had an average of 13.5. The absolute difference between these groups is 10.5. And therefore, that is a significant difference because the difference only has to be 5.01 points. So already we can say that the average difference between treatment 1 and treatment 3 is statistically significant. And then last but not least, let's compare treatments 2 to treatment 3. Treatment 2, the average was 4.5. For treatment 3, the average was 13.5. That's an absolute difference of 9. 9 is larger than your HSD value of 5.01, and so that is also significant. Okay, so that concludes this problem. Let's just summarize what we did and what we found. We were checking with analysis of variance, Anova, whether or not there's at least one mean difference between these 3 treatments. And our initial analysis of the Anova gave us a conclusion of reject the null hypothesis, which means yes, we believe there is at least one mean difference. We then measured the effect size with eta squared, and I erased that to save some room, but the interpretation was a very large effect. And then the last thing we did just now was we calculated Tukey's HSD as 5.01, and the differences between group 1 and group 2 was not significant. The difference between group 1 and group 1 and group 3 was statistically significant. And finally, the difference between treatment 2 and treatment 3 was also statistically significant. So there you have analysis of variance, from scratch, from the raw data, all the way through a post-hoc test. So take a look at the textbook for more examples, as well as the study guide, and let me know if you have questions.